Okay, guys, I guess we're gonna start. So thanks for coming, everybody. My name is Shay. I'm just gonna spend 1 or 2 minutes just who I am and what is this talk about and so on. So my name is Shay, as I already said. I've been a long time Linux guy. I'm actually one of the Linux guys in this .NET conference, I guess. My day-to-day is on Linux. I used to hate Microsoft and write Microsoft with a $ instead of the S back in the day. You can see that the world has changed a little bit now that I am actually doing this. I'm the lead dev of Npgsql, which is the .NET driver for Postgres, the Postgres database. I'm a Postgres guy, which is once again comes from the Linux world. I've been doing that for a long time, since 2012. It's when Adam was speaking this morning about the open source experience, I was a little bit reminded of my own. I just started in a company. We were using Postgres. I was using the driver on .NET on Mono on Linux, by the way. Very weird decisions. And never mind. And I found some bugs. Eventually, I just started, submitting bug fixes. First issues, then bug fixes, and eventually I ended up kind of taking over it. So it just happened like that in a very kind of organic way. And yeah, that led me kind of to where I am today. I also do the entity framework core provider for Postgres, which is built on top of it. So that's the ORM that Microsoft does. Nowadays, I am working for Microsoft. I joined the team in January, so I'm very new to Microsoft, working on these things basically. So I'm part of the entity framework team. If anybody here wants to talk about entity framework, regardless of Postgres or anything, then I'm also available for that. Yeah, just a few words. So what is Npgsql? Again, in very few words, this is not going to be a database talk. It's not going to be a Postgres talk. It is going to be a log-free programming talk, but just a few minutes so that we can get it out of the way. So it's an open source .NET driver for Postgres, which is one of the major databases. It implements ADO.NET, which is the standard database API of .NET. I'm just saying this because I'm going to use that word in the future. It's a fully asynchronous driver, which seems like it should be a very natural thing, but it is actually not a very natural thing. We still have some database drivers out there which are not, like Oracle and so on. So just so that you know, not the entire world has unfortunately made the transition to asynchronous programming. It's a fully binary driver. Once again, why am I even saying this? So databases are a bit of a sad story in the sense that many databases actually still are going to still communicate via text, which means that when you send an integer to a database or you read an integer from the database, in many cases, what is going to happen is that we're actually going to do an encoding of it in text and send that and have it parsed on the other side, which sounds really, I mean, maybe that doesn't sound so bad, but then think about datetimes, what it means to actually talk about datetimes in text. So if you go to MySQL, you would see a situation that is a little bit hybrid. Databases are a difficult subject, and with that, I will continue. It's a very fully featured driver. There are some very interesting features which we'll not discuss at all, so I will just continue. The focus has been there has been a big focus in recent years on high performance, which is what I'll be talking about. So it's quite a high performance oriented database driver. It seems that database drivers are a boring thing, and I also thought so when I kind of started contributing. It's amazing how much meat and how much interesting and fascinating things you can get to writing a database driver. Really, trust me, I didn't believe this to be the case. It is the case. You do a lot of very low-level networking, buffering. You have to do a lot of parsing. You have to think a lot about efficient networking and round trips. It's really a never-ending thing. I'm still working on it after now, I don't know, 6 years, and there's still so much to do. Sometimes I'm confused by the whole thing. This is from Microsoft build, not from this year, but from last year. Ben, for those who just went to his talk, talked about how at some point ASP.NET appeared in the TechEmpower benchmarks on the plain text benchmark. Suddenly, ASP.NET was there, and it was there on Linux, which was a very big shock to the whole thing. This was in round 13. This was a relatively early stage. Last year, we had round 16 of TechEmpower. And what you are seeing here, so there are the improvements in the plain text, and you can see on the left, that's the plain text one, then there's the JSON. But on the right, you see another benchmark, which we used to be quite bad at, which is called Fortunes, which is a more realistic, let's say, benchmark in TechEmpower, simply in the sense that it actually uses a database, because most applications do use a database. And what you can see here is that in last year we had, .NET, the stack, had a very big improvement on the database layer, on the database benchmark. This is not at all completely thanks to me. I mean, I just don't want any confusion. But a part of it is because of the database driver, which is, of course, a critical part in this infrastructure. So you have in this stack ASP.NET, obviously you have the application, but if you are talking to a database, you're also passing through a database driver where you can lose a lot of performance. You would be, again, surprised at how important a component this can be. Now, round 17 is the current round that is currently online. If you take a look at the Fortunes one, which again is considered a little bit the default standard kind of benchmark, you will see us in place number 6, which is quite a nice place to be in. I'll even say that some of those which are up there are a little bit exotic in the sense that they're not really like widely used, generally accepted web frameworks. H2O is in C, so if you want to write a web application in C, you are welcome to do so. I hope I will not be working for you. But still, I mean, of course, we are not the faster, but we are in a very good place. I'll just say that if you look at the current continuous benchmark results, we've actually slipped in the ranking. We have not become slower, but others have become a little bit faster. And I have some ideas on how to fix it, but that's a story for another presentation. So let's go directly into the actual subject that I want to talk about today. How many here have done any form of block-free programming in the world? Wow, that's super scary. That's super scary because I hope nobody would do it. Really? I'll talk to the organizers to lock you guys in the room afterwards. No, the issue is that this is typically one of the subjects where, when I was first doing this talk, there is a moral dilemma, an ethical dilemma, because if you teach people this, they're going to use it. If they are going to use it, this is one of the more dangerous techniques for doing anything, basically. It's extremely dangerous. It's extremely hard to get it right. A bit like multi-threading code, but even harder. So what I'm trying to say is don't try this at home, basically. This is a very interesting technique, but it should really only be used when you've proven to yourself that it is necessary. Really don't even think about this kind of programming unless you know that it's the only thing that you can do now and that you really need it. First, before we go into log-free, a few words about what is a database connection pool. So Adam, again, mentioned this morning for those who were in the Spanification talk about the array pool. So everybody knows the concept of a pool. Let's say you want memory buffers. You don't want to allocate them every time because you would be putting a lot of pressure on the garbage collector. Instead, what we want to do is that resource, whatever it is, it can be a byte array or a connection to a database. You want to be able to reuse them. So you have an operation to request or to rent an object from a pool. You use it for a time, and then you return it to the pool. And that's it. And by this, of course, you don't pay the overhead of creating it and freeing it. A database connection is a very different kind of thing compared to a memory pool, like a memory byte array or anything of that sort. Physical database connections are notoriously expensive to create in general in databases. First of all, because typically they are a TCP connection to some server somewhere on the other side of the network. In Postgres, by the way, the architecture is even more, because it's an old school Unix kind of architecture. It's basically going to spin up a process, not a thread, a process for every physical connection that you're going to do. I'm just saying this to give you an idea how critical it is to not create connections all the time. Every now and then I get an issue from a guy who just did not turn off pooling because he didn't understand what it was, and the application does not work. It cannot work basically without pooling. It's just does not work. So in general, in the .NET space, a database driver is expected to contain a pool. In some other architectures, that's not actually part of the role of the driver. If you look at JDBC in Java, it's supposed to be an external concern. You can also have a database connection pool outside of the process. There are many different architecture choices here, but in .NET, and this is actually a good thing in my opinion, it's a bit complicated. It is a good idea that you have an in-process memory connection pool. This really makes it the most efficient possible. But also what it means, what this is orienting us, is that the open and close operations for rent and return should be extremely well optimized. You should think in mind that you have a web application, it's very scalable, it's typically going to get a web request, do maybe one database operation, so it's going to open, get a full connection, perform just one thing, and then close it. The overhead of open and close should be extremely minimal. Okay, really, really extremely minimal. That's vital for a good application. It's also the one place, and this is starting to get us to the log-free area, it's the one place in an application, in a database driver, where you need to worry about synchronization, about multi-threading. Why? As soon as you've given out a connection to somebody from the pool, excuse me, that connection is not thread safe. Users cannot take the same connection and use it at the same time from two different threads. Obviously, a connection represents a TCP connection. You can't start writing and reading from two different threads. It's going to be a mess. So the moment the connection is gone out, no more need to worry about. That's the user's concern at this point. However, the tool itself must be, of course, fully synchronized. It's the one point where everything has to be correct in terms of multi-threaded. So I think you can see where this is going. When I first started a big optimization push that led to this TechEmpower results that you see here, we saw, I'm giving you some ideas on how to identify contention in your application. So if you want to make your application go faster, you start to look at it with a profiler, you start to understand what's going on. Sometimes the problem is going to be contention. That means that you have a lock somewhere in your application, and the lock is preventing your threads from running because they are waiting on some sort of shared resource, right? How are you typically going to see this kind of phenomenon? So if you use a profiler, many times, even without a profiler, you're going to see you're not reaching 100% CPU. Not reaching 100% CPU in itself is not a problem. Okay? It's possible that you're not reaching 100% CPU because you're waiting on some IO. You're waiting on the database to respond. But in our case, we saw that the network was not saturated. So we're not waiting because there's not enough cable to push our packets through. And when we're monitoring the CPU on the server side, we're also not seeing any sort of pressure there. If the server was on 100% CPU, then we know we're simply overloading it. But this benchmark does really very simple things, and the database can handle that very easily. So we're not seeing 100% CPU anywhere. We're not seeing the network saturated. What's going on, right? So there are many possible solutions to this kind of thing. Contention is not the only one, but contention is a pretty good indicator. It could be an indication for contention. Some profilers actually you look at today, and they will tell you very precisely how much time you're spending in contention. And the new performance counters also have this. So ETW, basically the new counter, DotNed counter, which was mentioned at some point today, which is a new thing coming in 3.0, allows you to see all kinds of events, like garbage collection and the size of the heaps. It also allows you to know more or less how much time was spent in monitor enter, which is basically the one that blocks on contention. I hope you more or less understand this idea of contention and locking and all this. I'm kind of assuming that it's there. So the first thing that you do when you reach this kind of situation is obviously take a look at your logs. Maybe in many cases, your logs are a little bit too wide. So you're locking more than you would have to. For example, one big rule is you should try to, for example, avoid doing IO while holding a log, because IO is super slow. This is also one reason why in general you cannot do async await within a lock. That's one of the reasons for this. It's not the main reason, but anyway. So the first thing that you have to do is to diagnose, analyze your logs, and make sure that you're not just holding them for too long. That's an easy fix. This I had already done in previous versions. At this point, the log scopes were already quite optimized. So at this point, there's the unfortunate question of do we absolutely have to have the logs in the first place, which is where we start to go into log-free programming, which is getting rid of your logs. Log-free programming simply means that you don't log. Okay? To fully make you understand this basically means that all the operations that you are doing are always interleaved. Anything that you are doing can be happening in parallel with everything. It's extremely hard to get a mental picture of exactly all the possibilities of everything. The whole point of logs is that you know that within this region, nothing else is going to be happening. And you are losing this thing that organizes our way of reasoning about programs. So it's a very, very chaotic way to think of a program. But unfortunately, sometimes it is this way. What does it mean in practice? In practice, at the lowest level, interlocked operations usually mean that you're using what is called the so-called interlocked CPU instructions to do some things atomically. So it turns out that modern CPUs, all CPUs, have instructions really on them that simply allow you to do certain atomic things. By atomic, of course, I mean to do, let's say, two operations that either both complete or none complete. So you will never have a situation like in databases where the first one complete and the second one fails. They will perform atomically. So the CPU itself is capable of doing certain very simple operations in an atomic way. Conceptually, you can consider this a bit like a lock. It's as if you are doing a lock around these two small operations, but the lock is happening inside the CPU in a very efficient way. All right, we'll go into the code very quickly. Now, I used to work in an office where we had this door, and we had this sign on the door. And this is not about log-free programming. The sign says, because you probably can see, you must be this tall to write multi-threaded code. Now, aside from France, who is here, I don't think anybody reached that height of the door, which basically means before touching multi-threaded code, be very careful, because multi-threading is very, very hard. Anybody who's done it knows that this is true. It's it's 10 times harder to do it properly without using logs. This is basically the message here, which is why I'm telling you, don't do this at home. Let's jump right in and take a look at what a database connection tool, what an operation looks like when it's log-free. So what you're seeing here is a simplified version of a rent operation. So in this scenario, we are assuming that there's going to be a maximum of, let's say, 100 connections, physical connections. We don't need to support an arbitrary number of connections. I'll talk about this in a second. So we have an array up there with a constant, new connection pool size. Now, every time somebody wants to get a connection from our pool, we're going to do a simple loop over this connection array. All right? The first thing is not very important. We are just simply going to check if it is null or not. So every slot in this array, it might have an idle connection, in which case we want to take it out, or it has null, in which case we move to the next slot. I hope that's clear. I should have started with this. It's just a list of idle connections. If it is completely empty, everything is null inside, that means there are no idle connections that we can use. So going back to this, the first if is basically checking if it is null. If it is null, then we have to move to the next slot by doing a continue. Now comes the fun part. Assuming that we saw that there is something there is an idle connection there, now we are going to use interlocked exchange. Interlocked exchange is an intrinsic. It's not one of the new ones. It's been there for a long time. It's a very basic CPU operation with intrinsic. What you're seeing here is this interlocked exchange operation does the following thing. It goes to idle, which is passed by reference. It puts the second value, which is null, inside that slot, and it takes out whatever was there and returns it from the function. And then you have it in con. There are two operations happening here atomically. One is to put something in that slot, and the other is to take something out of that slot. I hope that's clear. That's two operations. I could write it by hand without interlocked exchange, but then they would not be atomic, and then it could interfere with other operations happening at the same time. Now, you can see that after the con, I'm asking if what I got out was not a null, then I return the connection and everything is good. Why do I have to perform this if? Because here I did this check. So by the time I get here, I can sort of assume that there is no null there because I just checked it. But between these two times, I may have been preempted and somebody else may have already taken it. So by the time this interlocked exchange actually happens, maybe there was a null in there. So I'm putting a null and I'm taking out a null. It could happen because we're in log-free world territory. And in that case, this if would fail and we would simply continue. But if we did manage to get the connection out, we are also 100% sure that we managed to get the null in. Okay, so nobody else is going to get this connection out. This is the most important point. The worst thing that can happen in this pool is if two users, two threads, get the same connection out and they try to use it at the same time. Catastrophe. All right? So that's an example of a very simple interlocked operation. All right? We'll be making it a little bit more complicated very, very quickly. Now at the end, if we went through the entire list, we didn't find any connection, we create a new one and we return it. Is everything clear about this code?
Did you want to store the new connection?
I'm just returning it from the operation here, and the user has it.
But it's not put in the pool.
Right. I see. I see what you mean. The question. Yeah. In this very simplified kind of thing, the idea is that this is a new one. We create it. It will get disposed. Let's not discuss it for now, because you will see in any case that the actual implementation is not at all like this. This specific implementation, by the way, has the very big problem, because you asked, that it can create a potentially endless number of connections, right? Potentially, in theory. There is no upper bound on the number of physical connections that get created. This is a big no-no when talking about database connections. You can't just create 1,000, have like 1,000 connections created. But I'll get to that in a second, I promise. It is one of the more interesting things. Before talking about this, I think this thing has gone away. Okay, I'll switch to the keyboard. This is still working, that's good. Yeah. Let's take a look at what the return looks like. Return gives us an opportunity to talk about a more complex interlocked operation. Okay. Instead of seeing exchange here, now you are seeing a compare and exchange. So once again, we have a function. We are going to go through the entire idle list. The idea is, of course, to put the connection back into this list, right? But the situation is a little bit more complex. So I'll explain what this does, and then I'll explain why. Compare and exchange looks at that slot, idle I. It checks if that thing contains a null, which is the last operand, the last argument, then and only then it puts in the con inside. And it also returns what was originally in that cell. So it does a few things together in one operation. It does a check. Is this slot a null slot or not? And then it writes into it if that check succeeded. And in any case, it will return what was in that slot when I checked it. You can look at it, that's maybe 3 operations performed automatically. Why is this so important? So let's just think about it in your head for one second. If the slot already contains a connection, we don't want to overwrite it. Of course, we want to put it only if it's null. Only if that connection is null, then we want to write it. But we also have to know whether the operation succeeded or not. If there was a con there, and we didn't write it, then we need to know that we didn't write it so that we can go to the next slot and try to write it there. Okay, it's a complicated situation. Okay, but the general idea is that we're checking if it's null, and if it is, we're going to put that connection in that slot. And this is a way to simply return it to the idle list. Is everybody clear about this kind of thing? Yeah.
When you do the compare and exchange, do you get back the connection that was written by the other one, other thread at the same time, or you
at the time that the compare and exchange executed, you get what was in that slot before you wrote it, if you wrote it.
So you check it's null. Somebody else has put something in. You get their connection.
So if it's null, that means that I managed to put it inside. In this example, it means it was null, and therefore I can know that I managed to put it inside. The API looks a bit convoluted. In other languages, it will simply return a bool to say success or failure, which is a bit more conceptually easy to understand. But it's the same thing. Okay, it's just a way of telling you whether the operation succeeded or not. Okay. If you actually look at this in Sharp Labs, which is a very nice, you can put C# code. It's a web thing. You put C# code in it, and you can get the actual assembly that the JIT produces. You will see that typically, not always, these operations, exchange and compare and exchange, translate to a single CPU instruction. That's a very powerful thing. Not always. In some cases, it will be like a function call, but that's a different story. So it's really the best you can ever do is one CPU instruction in that sense. Just to give you an idea of how much these operations are very, very efficient. Okay? There is also no lock. We're not actually locking. We're not holding a lock. These two things are happening in parallel. All right? So there is no point at which one thread is blocking because it's, or whatever, goes into an async wait, which is even worse in a way, because another thread has the resource. I hope everybody understands the advantage of this. The previous version of this pool, basically, at some point, would simply, you want to rent, you want to get the connection out, let's log the whole structure, go through the 100 cells, see if there is a null or not, do all my bookkeeping. This is what is meant by contention, by having your application limited by contention. This is gone here, all right? Now, if it were only about this, then you would probably saying, okay, that's too easy, this talk is not really enough. So we are going to make this a little bit complicated. A question?
Is there a lock inside compare exchange?
Compare and exchange is a CPU instruction.
No implementation of that?
No, it's a CPU instruction. Conceptually, your question is actually quite correct. So there is a cache synchronization protocol between cores. I'm not really not an expert in this kind of low-level stuff, but of course the cores themselves have to communicate between themselves to make this happen. But this is not a lock in the normal sense of the word. Okay, it's we are in a different territory now. There is no lock in the sense of contention anymore. There is something else that is happening. All right. So to make this a little bit more complicated, now we are getting to your question also, Jonathan. So physical connections, once again, are extremely expensive. And again, when Adam was explaining about the array pool, which pools buffer arrays, it's fine, that if we go to the pool, we ask for a byte array, there is none, then we just create a new one. It's not a problem, right? The array the tool doesn't really have doesn't have to manage an upper limit. As far as I know, there's no feature like this because there's no requirement like this. Memory is relatively cheap, we can say, and there is no hard upper bound on anything. But with database connections, this is happening. The situation is very, very different. The constraints of the problem are different. Typically, you have one database. Then each connection that you perform on it is going to take a certain amount of resources. It takes memory. It takes resources on the server side. You are also going to typically have more than one client server talking to that database. Let's say you have 5 servers talking to the same database. You have to calculate the aggregate number of physical connections that you are doing. I hope this is clear. So the requirement in this kind of situation is to have a completely predictable maximum and to know that your application will never go over 100 connections. Is it clear for everybody why this is? Because database connections are not just memory. You can't just get more, remove it. If you start having a lot of like freedom and chaos here, at some point the database will simply crumble under the load. So we can't write our connection pool in this way. Does this maybe come back to work? Yeah, cool. Okay. So the requirement of the problem, again, this is a requirement for our connection pool, is that once we reach the maximum 100 connections, we need the operation to block, or more precisely, not to block in the synchronous sense, but to wait until a connection becomes available. All right? It's a very, very different behavior than a typical pool that you will encounter of memory or of other resources. Even more important, if you are entering this waiting state, it's quite important for all those who are waiting to be unblocked in FIFO order. Okay, so the first one who starts waiting should be the first one who gets the next connection that frees up. Otherwise, and this, it was also the state of the connection pool when I started was like this. You had a completely random release order, it was not FIFO, which means that the first guy who came maybe was the last one, depending on some random thing, which means that it would occasionally time out, or users would get completely unpredictable response times. So you also need FIFO semantics, FIFO release order on this kind of thing. So of course this is going to a very simple place. Alongside the idle list, which we already saw, we typically want to add a FIFO queue, some sort of waiting list. I'm going to jump over the nitty-gritty details, but right now the architecture that was chosen, it's not perfect. We have a queue. If you want to wait, basically you create a task completion source, which maybe you're familiar with. If you're not, it's not a big deal. You enqueue it into this thing. The release will take that task completion source and pass the message through it. So it will basically complete the task. It's just basically a thing that we put in the waiting list that represents the opening attempt. Let's say it like this. That's not the important part of the presentation. So if you're not aware of what the task completion source is, it's not the end of the world. Now, to understand the constraint, so when somebody releases, it means we can't just go and put something into the pool because somebody may be waiting right now. There may be pending waiting attempts, right? Yeah, now we've added this additional thing. So when a connection is being released, first I go to this queue. I'm going to check, is there anybody waiting for it? If so, of course, they get to have it first. We can't just put it in the idle list. It has to go to that person who is waiting. So we dequeue the first one, FIFO order, as we said, and we give him that connection. This is basically what we're trying to achieve. Ordinarily, this would be quite easy to achieve in a normal application using a lock, but lock-free. So we have two data structures, and we're not allowed to use locks, basically. How do we do this kind of thing? So we have one idle list, we have one waiting queue. Everything happens here in parallel. So the moment that we update one, by that time the situation has changed around us because there are no locks. So okay, this is just maybe I can give an example just to give an idea of the kind of race conditions that we have. Let's say that somebody tries to get a connection, but there are no idle connections right now, okay? So it goes into the waiting queue. It's going to wait until somebody releases a connection. But at the exact same time, somebody is releasing a connection. At the same time, there's a race condition, and the connection ends up in the idle list, okay? Because we have no locks. So now the situation is we have one connection in the idle list, and we have a connection attempt in the waiting list, and they will never meet. You understand? This basically will be blocked forever. It's just to give an idea of the kind of problem. Basically, imagine any concurrent, any multi-threading application where you have no lock. everything is competing and in a race condition against everything else. How do you solve this kind of problem? Basically, you need to have one picture of the state of your connection pool, how many connections are idle, how many are busy, and how many are waiting. You need to have these three values somewhere, you need to track them, and you need to be able to make modifications to them atomically. All right, this is the challenge. So I hope this is clear. If you know at any given point exactly how many idle, busy, and waiting connections you have, you can kind of get out of this alive. This is basically what you need in order to solve this problem. But you have to have a 100% consistent view of these three. They have to be always in sync. All right. So how do we do this? So we have multiple counters. We want to manipulate them atomically. Adam showed something very similar to this. He discussed struct layout. So what we do, this is a bit of a trick, but it's a nice trick. I hope that you will like it. We have something called the struct layout in C#. Okay, I'm repeating Adam's point from this morning. Basically, it means that instead of allowing C# to order the struct in the way that it sees fit, we are going to say explicitly exactly where each field is going to start and where, basically, and that's it. Okay, we're going to order the fields ourselves in memory. So what you see here, we have one idle, one busy, and one waiting. We have three counters. Their data type is short, which means 2 bytes. We are placing them one after the other, 0, 2, and 4. But then we also have one long, which is 8 bytes long, and it is placed on position 0. The point here is that there is an overlap between the long, which is called all in this struct, and the smaller counters. They are taking up the same memory. Okay? If I go and change idle, then I'm also changing all, and vice versa. This is called a non-discriminated union. This is in C, you actually have a union to express this kind of thing. This is how you do it in C#. Now, how does it help us in our problem? This is the interesting thing. So I'm working my way towards this. There are several steps. So we have this struct called pool state. The idea is this. I'm going to take the new state, and I'm going to copy it to the stack. So let's say there is an underscore state, which is the state of the pool, the actual state of the pool. I'm going to copy it to the stack via one mechanism. So I'm copying the all like this. This means I'm basically copying the entire struct because all encompasses the entire stack, the entire struct. All right. So we took a copy of this state variable into our private stack of our thread. Now we are free to manipulate it as we want, right? So we decrease the idle and we increase the busy. These two changes, they must go together. They are atomic. They should be atomic, right? And at the end, we are going to commit the changes. It's really helpful to think about databases in this context. You are doing something atomically with like a transaction and committing them. So committing means taking what we did in our stack with the changes and writing them back to the global, whatever, to the pool. All right? But this is, of course, not enough. We still have a race condition here because we copied the state and now we're manipulating it. But because we are in the chaotic world of lock-free, somebody else may have copied it as well. And we're doing it at the same time. And so I will overwrite his changes. We can't write code like this, of course, without some sort of synchronization, which brings us more or less to what I wanted to show. How do we handle a race condition? This is really how lock-free programming looks like now. What you are seeing, it's a bit complex, but I will go through it one by one. Ignore the spin wait for 1 second. We have an endless loop here, while true. All right? The while true will do the thing that you just saw. So we copy again, ignore the volatile read for 1 second. Basically, we copy the state, underscore state, into the thing called old state. So we did a copy of the old state into our stack. Now we create a copy of that called new state, where we're going to do our changes. We decrease the idle, increase the busy. So we do the actual change that we want to do now. So we're changing that memory in our stack at this point. And now we are going to use a compare and exchange to write it back to the pool, basically to change the state of the pool. So what we are now saying, if you look at this compare and exchange, we're putting everything together. The new version of the state, which is the version where I've decreased idle and increased busy. This new version, write it as the new state of the pool, but only if that state hasn't changed in the meantime. This is what compare and exchange actually does. If underscore state hasn't changed in the meantime, then what we will get out of the interlocked compare and exchange is the old state. In other words, the compare and exchange succeeded. If it succeeded, then you see we get to the break and we have finished. So we have managed to update our two counters in a way that was atomic. All right? If we have failed and somebody else in the meantime has done an update, then what will happen?
Try again.
We'll not get the old state anymore. So this check will fail. The thing coming out of the interlocked compare and exchange is no longer equal to the old state because it has changed in the meantime. And so what we will do is continue in the while true. This is an endless loop that attempts every time. Basically, it's an endless loop. I copy the current state, make the change, and try to commit it back. But I may fail because somebody has changed it in the meantime. So I discard it, and I copy it again, try to change it, and try to write it back. This is basically what log-free programming is. It's a bunch of loops all the time. It's a bunch of endless loops that attempt to make a change with using interlocked operations. All right? This code will spin, what we call, it will basically spin. It will do an endless loop until it manages to actually perform its job. All right? Now, a few comments on this. One trick here is that the first trick that we do here is the fact that we use a non-discriminated union to have the counters on the one hand and one value that represents them on the other hand. So when we want to change the counters, of course, we want to talk about idle and busy. But when we want to commit the changes with the interlocked operation, then we need just one variable. I can't do interlocked on two things atomically. That's the whole point. I can only do interlocked on one thing. And that one thing is the piece of memory of 8 bytes that encompasses all of these counters. I hope that that's clear. So basically, when you want to wrap more than one value for atomic operations, you can use this trick. It's just, it's a trick. Then, forget about this. You could have even, maybe even you didn't have 3 counters. You maybe had only 1 counter. Then you can still use, in any case, you can use the compare and exchange to go into an endless loop and every time do your change and attempt to write it back. Do your change and attempt to write it back.
Which is another form of contention that you just done.
It's another form of contention, exactly. It is another form of contention, but it's the most reduced and efficient form of contention you can do. It's
yeah. In the end, the problem is that you have one resource.
Yeah,
you all need to change.
Exactly.
At some point.
We're never going to get rid of the fact that there is the state of the tool, and that is one thing that multiple threads are going to be manipulated. Maybe I'll finish 2 more sentences and then I'll open it. Don't worry, I won't move from this slide before I hear all your questions. Just 2 more things that we need to know here. So you see that this is a tight loop. You can actually just do a while true, but the problem is that in some cases it might take a while and you don't want to burn the CPU. Not in the ecological sense, but in the sense that you are making it busy and not available for other things. This is why there's a very cool utility in .NET. This is a .NET tool called spinwait. Basically, it's a thing that is meant exactly for this. Spinwait is a thing. You see that I'm calling spin once every time that I'm spinning. Spin once basically knows inside how many times we've already spun. In the beginning, it will just make you loop like a spin. But after a while, it's going to say, okay, this is actually taking a long time. Let's stop spinning. Maybe we should yield. Yield means yielding the thread. Okay, so that the thread is scheduled to run a bit later. So basically, it's an intelligent way to not spin for a long time. You're spinning for a short time, and then you will not be spinning anymore. Okay, it's a way to make your compare and exchange loop a little bit more easy on the CPU, a bit more efficient. If you didn't understand this, it's not fundamental. It's not like a fundamental part of this technique. It's just a way to spin in a better way. And then the volatile read that you see here, this one I really won't go into it too much, but at the very least, you are telling the compiler that this value, even though it might seem like it's never changing, is actually volatile and might get changed by some other thread running on another core. So it should never be optimized into a register or something like this. Basically, you're telling the compiler and the JIT to always read that value. But never mind about this. These are the details. Questions about this? Yes.
So you said this works on 8 bytes. What if I need to store more states?
Great question. Yeah, I think I even have some points here. Yeah, I'm not even sure. It's a great question. This will only work until 8 bytes on a 64-bit system. When you need to do something more, one option is going to be to allocate another structure, which can be as much as big as you want. And then you are going to do the compare and exchange on the reference.
Yeah.
But then you have to manage the allocations, right?
Yeah.
To pull them in some way, so it gets complicated. The problem is that this tool, it's a CPU instruction. It's not going to, it's going to work on 8 bytes. The guarantee is only for 8 bytes. I will say that actually CPUs have, all modern CPUs have 128-bit compare and exchange operations, but I'm not aware of any way to, that they're exposed in .NET. Maybe one of those guys over there.
The problem with them is they have to be aligned on 16-byte boundaries.
Okay.
You can't, .NET aligns pointer boundaries.
Okay.
64-bit boundaries. So otherwise, the CPU fault would be crossed.
Makes sense. Maybe one day there will be some sort of.
There's an issue for it.
Cool. I'm sure there is. So yeah, in theory, it could be possible to do this on 128, 128. Okay, but anyway. There was another question.
I have the same question.
Same question? Yeah. Yeah, I mean, the answers are not great in this kind of thing because we're dealing with very low-level things. Basically, you kind of encapsulate it in another object and deal with the problems of the allocation. I'm not aware of another.
Just as a follow-up, did you have like a actual need to use more than 64 bits for your counters?
Me? I actually didn't even need 8, I just needed 6. I had 3 short point. I mean, again, I was assuming that I never have to deal with more than a short number of connections. But this is my scenario of database connections. Another scenario, who knows? Okay, so this is a trick that is quite tailored to this this kind of thing, but it will help in a surprising number of cases, I think. All right. Other questions about this?
I have a question.
Oh no, not from Adam. Shit.
How did you come up with this trick? Do you have some good book to recommend that treats that what programming?
I think I had like a blog post or two. I'm not sure if I saw specifically the non-discriminated union trick combination with interlocked. I don't remember, to be completely honest.
You don't need it per se, right?
Sorry.
It would just be bit twiddling otherwise. If you didn't do the union.
I could do it with bit twiddling. So we could just have one long, and then instead of using the non-discriminated union, we could just do the bits. It's true. Yeah. But this way is nice.
Absolutely.
It's basically the same as an update with concurrent where clause in the database. Basically the same.
You could say that exactly. Exactly. Basically, the idea is what we call optimistic concurrency sometimes, which basically it's going to fail if somebody has already modified. Conceptually, this is exactly the same thing. Yeah, but with memory and CPU. Exactly right. Actually, there's a lot of database analogies to be made with this programming model. So if you are good with databases, then it's a good way to think about these things. It's true. Yeah.
How many items were typically in the list?
So specifically Postgres, yeah.
Yes, because we're doing this because taking a lock and going through the list was slow, causing a bottleneck. So how many items were like in this list?
We are talking, so a typical application with Postgres. So we're talking now very specifically about this database with really maximum in the low number of hundreds, and that's already a lot. Okay. In the end, this was an empirical investigation. So I did this investigation, and this turned out much faster. So it turns out that scanning an array that is quite big, like this,
With 100, with just 100 object references was causing a bottleneck.
it can happen, of course. Of course, we have locality of reference. It's an array, so they are filling in the cache line. So this is why it can run fast. But of course, as the array grows, this technique will no longer work. It's true. There are many very specific assumptions here in this case. It's true. Yeah.
Do you check for overflow on the short waiting? Right.
I don't. But once again,
so
what I do check.
DotNed, if you crank up the connections high enough.
But wait, there is a maximum. The maximum pool size is checked for a maximum.
Yeah, the pool size. But not the waiting.
But
the waitings are coming from requests.
Yeah, this is true. Yeah,
So
this is we have we have
you
not
could
gotten-
actually, okay.
This could happen. Yeah, actually, it should be an int. We have the
Yeah.
2 spare bytes. That's a good.
Yeah, that's
see,
good.
the guy is giving already a good improvement. That's true, actually. I'm interesting that nobody has gotten to it.
Yeah, yeah, I think
It's a good
that's,
point. Busy and idle can be short, so that the
if
other
we
one
go
should
to
be
the 40 gigabit machines, we might hit it.
interesting comments. I'm open at the art.
Yes, I will.
No, really, it's a very good. Unless there's other questions, this is more or less. I mean, I had some other content possibly. I will just say, because this is now more or less the end of the time. There is something called the ABA problem, but I won't discuss it now because we're out of time. The techniques with log-free programming always potentially suffer from it. In this case, there is no ABA problem, so it is fine. I'll just skip over this. This was just an idea, just to give the kind of race conditions that we have to deal with. But we are a little bit out of time, and I think everybody understood how dangerous this was. Basically, don't pre-optimize. What I'm trying to say as a conclusion, this in the end alone gave around 8% an 8% increase. It's definitely the most dangerous 8% I personally ever coded. With log-free, you are never actually sure that your code doesn't contain bugs. That's basically the problem. There is no way to know. It's like a more severe version of multi-threading code. You just can't know, and you never feel secure. So even today, I come to a conference, and I'm afraid somebody will stand up and say, "Yeah, but what about this case and that case?" And you are like, "Ah, shit, I didn't know about it." Really, it's really when you go into the details, if you actually look at this code, you will see that it's not good. Therefore, I really say no to log-free algorithms, say yes to pizza. Really, honestly, I really don't recommend going into this unless you've proven that it is really the right thing to do. Don't do it. Just don't. If you think you need to do it, don't do it. Then maybe, yeah.
Is there somewhere an overview of all the atomic operations in .NET? Because
Go to
interlock.
the interlock class in the API docs, basically. Most of them, look, you have stuff like increment and decrement, which basically does ++ in an atomic way. Even ++ is not atomic when you think about it, right? There's 2 things. You read it, you increment it, and you write it. So even this, if you want to do it, you have to use interlocked increment on it. You have this, you have exchange, compare and exchange. Those are the main ones, but take a look at that class and you will see the others. It's relatively easy to understand. It's not like, there's nothing complicated there. The compare and exchange is actually the most complicated that you will see. That's it? Okay. Yeah, another one.
So do all CPUs actually implement all the different interlock operations? Or,
Which one, sorry?
I don't know if every interlock operation supported by .NET is actually implemented by every CPU.
So what the .NET API exposes is the set that is widely available on all modern CPUs. In interlock, unlike some of the intrinsics that are coming out in 3.0, all of these, everything you will find on the interlock class has been there for a long time and is universally supported. These things, by the way, are back. It's not like a cool new .NET Core optimization. They have been there since .NET Framework 1, 2. I don't know.
What are the
One.
Do you know if they are shimmed? If you run on x86 and you put in a long,
Sorry?
if they are shimmed then.
Oh no! So you cannot do an interlocked exchange on 32 bits. Yeah, or for an 8 byte. Sorry, in this case, so you cannot do it on the CPU level.
Yeah, so they shim it, right?
They shim it with something else. Exactly.
Yeah.
So it is safe but inefficient.
Yes.
If I remember, I looked into this once. Yeah, they shim it.
Yeah.
Anything else? Okay, just a few links in case anybody is interested. This is the link to my slide, which is online, just in case one of you guys is interested. And the link to the project, documentation, whatever, Twitter. If you're interested, yeah, you can come talk to me. Thank you for listening.